It's your presentation.
Okay, and now I can share, right?
Yes.
Okay, and it works, right?
Okay.
And does it work like this? No. And like this it works. Okay, right. Okay, so if you tell me that you hear me well, we can start whenever you want.
Yes.
Okay. Hi everyone. Thank you for the invitation and the opportunity to give a talk here. So today I would like to introduce you briefly to a topic that in geometric group theory that is very nice, which is the theme of scaling quasi-isometries. And briefly, I would like to show you how this geometric concept, this geometric object, can be used to derive some very nice and elementary statements in group theory, completely algebraic statements from completely geometric tools. Okay. So the two objects we will deal with today um, are quasi-isometries and wreath products. So the definition will be quick, but let me just recall that in geometric group theory, so we like to look at finitely generated group from the large scale point of view, meaning that if we fix a finite generating set for a finitely generated group G, we can define what is called the world length of an element G with respect to this generating set, just as being the minimal number of generators that you need to write your group element as a product. And as soon as you have this word length with respect to this generating set, you can define what is called the word metric associated to S of G, just by declaring that the distance between two group elements G and H is the word length of the element G minus 1 H. So the elements that you need when you multiply G from the right by this element, you land at H. And so now that we have this metric structure, we can look at the family of maps that preserves this structure. So you fix two finitely generated groups with fixed generating sets, and you call a map F between G and H, you call it a quasi-isometry if um, it, uh, it does not need to preserve the distances, but it does not deform too much the distances between two images, okay? So a way of formulating this is that you can find constants C and K such that these two inequality hold. So you should be able to bound from above and from below the distance between two images in terms of a fine function of the distance between the pre-images. So this is the first requirement that we need. So when the map F satisfies the first point, we call it a quasi-isometric embedding. And to ensure just an invertibility, a way of inverting the map in some category, we add the second point, which is a condition of quasi-density of the image in the target. Namely, we ask any element of H to be at a uniform bounded distance from the image of F. Okay, so this is really just to be able to invert the map. And another way of reformulating the definition is to say that a quasi-isometry is a map which is a quasi-isometric embedding. So you have the two first inequalities, and it has what is called a quasi-inverse. So it is a map that goes now from H to G, and such that the composition that you may take are at a bounded distance from the respective identities. Okay, so you can write this as follows, where how do you define the distance between two maps that are defined over G? It is just the L infinity distance, the uniform norm. So you just declare that the distance between H1 and H2, it is the supremum of all G in G of the distances in H between H1 of G and H2 of G. So this is the first object that we need to talk about the object we are interesting today. The second concept we need is the one of a wreath product of groups. So the notion of quasi-isometry is the geometric part, and the notion of wreath product is the algebraic part. So the wreath product, perhaps that you know it already, but it's a construction that allows you to get a new group out of two group G and H, and this new group will contain G and H as subgroups. So what do? You form a semi-direct product where the first factor is a direct sum of copies of G indexed by H, and the second factor, the right factor, is just a copy of H. And to take the semi-direct product, you just need an action of the second factor on the first factor. And here, so the first factor is a set of functions defined on H with values in G. So since H acts on itself by left multiplication, it also acts naturally on the set of functions that are defined on H just by shifting the argument of the function inside. So if you see rather this as sequences indexed by H, you can just say that H acts on the direct sum by permuting the coordinates by left multiplication. So this is a construction which is possible for any two groups. No requirements are needed. But inside geometric group theory, if you now start with two finitely generated groups, you can see that the wreath product will be also finitely generated. And in fact, you can explicitly construct finite generating set. So for instance, you can check that this guy is the generating set of the wreath product. So the second part, it is the easiest one. It is just a copy of the generating set of H because the law of the semi-direct product in the second component, it is just the law of H. So here you do nothing special. So you can just take S of H and you are good to generate the second factor in the wreath product. And the first factor, you can check that it is enough to take this function delta of A. So you should think of them as Dirac masses. So delta of A is a function that goes from H to G, and that sends the neutral element of H to the element A, and that sends any other non-trivial element of H to the trivial element of G. Okay, and you can check that with the law of the wreath product that this finite set actually is enough to generate the whole wreath product. And so now, as soon as we have generating set, so we have well-defined word metric and well-defined word length. So we have a metric space at hand, and we may ask when are two wreath products quasi-isometric. Okay, so I fix G1, H1, G2, H2 finitely generated groups, and I'm looking at quasi-isometry between wreath products. And there have been some developments on this question, some very, very interesting developments. But the question in general is still widely open, and there are many, many cases that we just don't have any idea of what could be an answer. But for today, I just want to insist on one recent development in a special case, because it is the important result that lead to talk about scaling quasi-isometry. So the result is due to Anthony Genevois and Romain Tessera, and they offer a complete answer to the previous question in a specific case. So the case is that first they restrict to Lamplighter, so meaning that they suppose that G1 and G2 are finite groups. Okay, so still it is a very interesting case, and Lamplighters are also intensively studied in group theory. So they suppose G1 and G2 finite. So here in the statement, I call them rather F1 and F2. And now the base groups, they also assume that they are finitely presented and one-ended. Okay, so these two assumptions, they are a bit restrictive. Okay, there are cases that are not covered at all by the theorem, of course, but there are also many classical cases that were not covered earlier, and for which we now know a complete classification. Okay, so the criterion of Genova and Tessera is in two parts. There is an amenable situation and a non-amenable situation. So the non-amenable situation is the less rigid one, because here the criterion is only saying that your two wreath products are quasi-isometric if and only if two things happen. So the first is an arithmetic condition on the cardinalities of the Lemma group. So you need these two cardinalities to have the same prime divisors, actually. And the second condition is the existence of a quasi-isometry between the base group G1 and G2. And from these two data, you can recover a quasi-isometry between the wreath products. Okay, and these two data are sufficient and necessary. But just for now, keep in mind that in the non-amenable case, these two conditions, they look completely independent of each other. You see, there is no interaction between the quasi-isometry here and the cardinalities of the Lemma group, or at least at first glance. The amenable situation is more rigid because here the criterion is saying that your two wreath products are quasi-isometric if and only if you have a stronger condition on the cardinalities of the Lemma group, which is that they must be power of a common numbers. Okay, so you may express this as saying that you have integer a, r, and s such that these two equalities hold. And on the base group, you also ask the existence of a quasi-isometry, but not any quasi-isometry. This quasi-isometry must satisfy an additional property, which is of being quasi S over R to 1. Okay, so this is exactly this terminology which is called scaling. So I will define it in 30 seconds. But for now, just also observe that in the amenable situation, you have clearly a dependency between the two conditions. Okay, so the quasi-isometry that you find between the base group, it must be compatible in some sense with the cardinalities of the Lemma group with the exponent R and S that you find here. Okay. So now it is this terminology in the statement that I want to explain with some details. So it is what are called scaling quasi-isometry. So the idea is to say that a map between two finitely generated groups, a quasi-isometry between two such groups, is quasi k to 1 if you have this condition. So if you can find a constant such that you can control the difference between the cardinalities of a preimage of a finite set and k times the cardinality of this finite set. And you can control this difference by the constants you find times the cardinality of the boundary of A. Okay, so informally, the idea is to say that you map, the size of the fiber of your map, the size of preimages of points, roughly, they are roughly k. Okay, so up to a small error that you control, and you ask in fact a precise control, which is in terms of the size of the boundary of finite subset. And here the boundary, it is the classical definition. So it is the set of all H in the complement of A that lie at distance 1 from an element of A. Okay, so just keep in mind that this condition of being quasi k to 1 or measure scaling, it is in fact a way of quantifying the default of your map to be injective if you want. Okay, roughly it says that the fiber have cardinality k up to a small error. And in this case, the real number k, so here k is a real number, it is important. It is not necessarily an integer. It can be 3 over 2 or 1/2 of really any strictly positive real number that you like. And it is what we call the scaling factor. Okay. And one other motivation for this notion is a famous result of Kevin White that explains at least partially the terminology. And White showed that a quasi-isometry is quasi one-to-one. So in this sense, with this inequality, if and only if it is at a bounded distance from a bijection. Okay, so it is not exactly a bijection, it is not necessarily one-to-one, but up to a small finite distance change, you can recover a bijection. Okay. So this is why we call this map quasi K to one. Okay. Um, Another remark that we can make is that the definition is not interesting for non-amenable spaces. Okay, you can check that because in non-amenable spaces, boundaries of finite subset, they tend to be rather big. Okay, so this inequality, in fact, you can check that for any k, it will be satisfied. It is just a use of a triangle inequality and the definition of non-amenability, and you always have this inequality for any k. Okay, so in order for scaling map to be an interesting notion, we should restrict to amenable spaces. And for amenable spaces, it is much more interesting because here you can check also by a direct computation that the scaling factor, if it exists, it is unique. Okay, so if you have a quasi-isometry between amenable finitely generated group, which is both quasi k to 1 and quasi k prime to 1, you can check that in fact k must coincide with k prime. Okay. So here it is completely, first, it has no reason to exist. So there are quasi-isometry between amenable spaces that are not scaling. But when it exists, the scaling factor is unique. Okay. Um, okay. And also the main example for you to keep in mind, I think, it is really an elementary example, but already a non-trivial one. You can check again by computation that if you take a finite index subgroup of an amenable group, the natural inclusion is always scaling, and the scaling factor is precisely 1 over the index. Okay, so, and in fact, this example is already enough for us to derive the algebraic consequences that I was mentioning earlier, and that we will see at the end of the talk. Other properties for scaling map that contribute to motivate the introduction of the notion is that the scaling factor, it behaves very well with respect to the classical operation that we like on quasi-isometry. So first, you can check if you want, again by computation, that the scaling factor is invariant under finite distance change. Okay, so if you start with a quasi k to 1 map, and you take a map which is at a bounded distance from f, then this map is also quasi k to 1. Okay. The second operation that we like very much on quasi-isometry is composition. And the scaling factor also respects composition in the sense that if you have a quasi k to 1 map and you compose it with a quasi k prime to 1 map, then the composition will also be scaling, and the scaling factor is exactly the product of the initial scaling factors. And lastly, with respect to quasi-inverses, it also goes very well because if you start with a quasi k to 1 map from G to H, then you can check that any of its quasi-inverses will be scaling, and it will be scaling for the scaling factor 1 over k. Okay, and so if we sum up this proposition in one observation, in fact, it is saying that when you look at an amenable group, an amenable finitely generated group, you have a well-defined group morphism, which is called the scaling morphism, and that sends any scaling self-quasi-isometry of the group to its scaling factor. Okay, and it is well defined because we said that in the amenable case, the scaling factor is unique. Okay, so this is well defined, and the properties with respect to composition, in fact, it is exactly saying that this map, the scaling map, is a group morphism. And when you have a group morphism, so you can look at its direct image. So here it will be a subgroup of half the real line, okay, of strictly positive real numbers equipped with the multiplication. And so this subgroup, it is associated to G in a canonical way, and we call it the scaling group of G. Okay, so in fact, it is the group, it is the subgroup of the strictly positive real numbers that encodes all the scaling behavior that we can have for our space. Okay. And so now that this object is defined, so there are mainly two questions we are interested in. So the first one is, given a G, an amenable finitely generated group, is it possible, perhaps, to compute the scaling group of G? Okay, is it possible? And if yes, is it harder or is it simple um, or yeah, what are the methods for computing the scaling group? And even before the scaling group, in fact, it is already interesting to wonder whether any self-quasi-isometry of your group is measure scaling actually. Okay. So just before the computation of the scaling group, this question is already interesting. And we already know the answer to these two questions in some cases. Okay, so in the article where they introduced the notion, Genevois and Tessera computed some scaling group for some group where we know the behavior of quasi-isometry. So for instance, you can check that for Euclidean spaces, if you look at homothéses, it is already enough to see that the scaling group of RD is the whole line, the whole strictly positive real numbers. Okay, and it is also possible to show that the scaling group of, for instance, solvable Bohm-Slack-Solitar group, it is also the whole of R. Okay. On the other hand, um, we can also notice that it follows from their classification results that the behavior is completely opposite for wreath product for Lamplighter over one-ended groups, because it follows from their strategy of proof that under our assumption, so you take G1 and G2 finitely presented, amenable, and one-ended, it follows from their strategy of proof that, in fact, any quasi-isometry between two such Lamplighters is measure scaling. And so the computation of the scaling factor is explicit. It is S over R, where S and R are the exponents that you find in the cardinalities of the Lamp group. Okay, so it is in fact a direct consequence of their classification. And in particular, you can notice that for such wreath products, so when G is amenable, finitely presented, and one-ended, and F is finite, okay, so here it is true for finite groups, the scaling group is reduced to one, okay? It is the trivial subgroup of the strictly positive real numbers, okay? So in other words, it says that as soon as you look at the self-quasi-isometry of this group of F ref G, actually it is always at bounded distance from a bijection, okay? So this is quite a strong rigidity phenomenon, which is not true for many amenable groups, in fact. So what I propose to explain you now in the remaining time is a slight extension of this result, actually, that I proved recently. But now, so what is changing is the cardinalities of the Lamp group. So here the results involves Lamplighters, but with lamps of polynomial growth. Okay, so now the lamp can be completely infinite. And the result is the following. So you take two polynomial growth groups of growth degrees n and m, and now you take two base groups with some assumption. So the assumption of being finitely presented remains. You also need amenability because, okay, it is not restrictive to suppose that the group are amenable because, as we said, if they are not amenable, the statement is completely empty and you are quasi Ket1 for any K that you like, okay? But the important assumption is that these two groups must be from a certain class that I cannot introduce in details right now, okay? But I call it M of X. And the claim is that under these assumptions, any quasi-isometry between two such Lamplighters with lamps of polynomial groups will be scaling. And it is scaling for a scaling factor that you can compute explicitly. In fact, it is just the ratio of the growth degrees. Okay? So any such quasi-isometry is quasi m over r, m over n to 1. And this class m of x, so I cannot tell you in detail what it is, but I can already tell you that it contains many examples of such finitely presented amenable groups. Okay, so for instance, they in fact introduced it very recently with another collaborator, and they showed that, for instance, all the solvable Baum-Slack solitaire group are in this class. You can also take direct products with amenable finitely presented group, and you can apply the theorem to such group. There are also Lamplighters over amenable groups. So, for instance, this with product. There are also Sol and other Sol-like groups, if you know the group Sol and its relatives. So it contains many finitely presented amenable groups. And as a direct consequence, in fact, it is what I had in mind when starting working on the subject. It is also true that such Riff products, so with length of polynomial growth, they also have scaling group reduced to one actually. Okay, so here also it is true that any self quasi-isometry of this space actually lies at the bounded distance from the identity. Sorry,
Sorry,
at a bounded distance from a bijection.
sorry for interruption. Your time is running out.
My time is out?
Yes.
Already. Okay. So I mean it was the main theorem, so it is okay if I stop here. So yeah. Yeah, okay. So if I stop here, you tell me, or if I can continue perhaps for 2 minutes, you tell me also. It is like you want.